Well, welcome to lesson 4.5 on the graphs of tangent, cotangent, secant, and cosecant functions. My learning targets for this lesson for you is to be able to graph each of these functions and also describe any graph transformations related to those functions. So we've talked pretty extensively about how to graph the sine and cosine functions and their transformations. So in this lesson, we're going to start out with the tangent function and explore its graph and graph transformations of that function. And the tangent function is defined as the sine over the cosine. That's the basic definition of the tangent function. So a couple of things happen with the graph of the tangent function. So one of the things that you'll notice is when you have a sine wave, okay, anywhere where the sine is 0, the tangent will also be 0. So you'll notice that 0, 0, and at pi we get a 0, and then again at 2 pi. And then with the cosine function, we'll also notice a similar kind of a thing. Whenever the cosine is 0, it would make sense from the equation that if the cosine is 0, the tangent function will be undefined. So when our cosine wave is 0, that's when we're going to get a vertical asymptote for the tangent function. So all of our vertical asymptotes will occur when the cosine is 0, and all of our zeros will occur when the sine function is 0. And the zeros happen at the integer multiples of pi, so at 0 pi, 2 pi, 3 pi, and so on. And the one thing to notice about the graph of the tangent function is the period is different from the sine and the cosine functions. So we have our graph, if we start at 0, we get the positive end of this thing, and then it repeats again at pi radians. So we get a full cycle of this thing in pi radians. Its period is pi rather than 2 pi. So when you're calculating the period of the tangent function, rather than using the 2 pi over the absolute value of b, you're going to use pi over the absolute value of b. And another point I wanted to make here in the last sentence on this slide, there's no amplitude or phase shift for tangent functions. So we don't talk about the amplitude or phase shifting for these. We talk about horizontal translations and vertical stretches and things like that. So let's go ahead and take a look at what a problem might look like for tangent. This problem says to graph y equals negative tangent 2x and describe the transformations. Well, we've got the negative out front, so we know we're going to have a reflection across the x-axis, and the 2 inside of the function will give us a horizontal shrink by a half. So this first graph that I have for you is the parent function of the tangent. So remember that one repeats every pi radians. So if we go ahead and reflect that across the x-axis, here's what our graph would look like. So we're going to shrink this thing horizontally, so our period now becomes pi over 4. And remember we said we could do that by taking pi divided by whatever b is. And normally that's pi over 2, but since this one has a horizontal shrink by a half, then we're going to get pi over 4 as our period. All right, the cotangent function, excuse me, the cotangent function is just the reciprocal of the tangent function, and here's what that function looks like. When you look at your sine wave, whenever we have the sine being 0, okay, at all of those points, when the sine function is 0, that's where we're going to get our vertical asymptotes, and we've got some of those drawn in here. And then when our cosine function is 0, here's the red cosine function, whenever that's 0, that's where our cotangent function is 0 as well. So our vertical asymptotes occur when the sine is 0, and the zeros occur when the cosine function is 0. And then our period is again pi radians rather than 2 pi radians. So here's an example of a problem dealing with the cotangent function. We are supposed to graph this thing and describe the transformations. Well, I've drawn in the graph of the parent function y equals cotangent x for you. The period, again, we're going to take pi divided by b, and b in this case is a half. So pi divided by a half will give us 2 pi for our period. So normally our period is pi over 2 pi radians. This time it's going to be 2 pi radians, so it's going to be horizontally stretched, right? So we also have the 3 outside the function, which is a vertical stretch. There's our horizontal stretch by 2. And then we also have a vertical translation up 1 unit. That's what the +1 is doing. And our vertical asymptotes will happen at even multiples of pi. So here's an example of what that curve will look like with all of those transformations. The secant function is the reciprocal of cosine. So when we look at the secant function, I've got the cosine function drawn in here in a dotted line. And whenever that cosine function is equal to 1 right here, we have the same value for secant. That should make sense. 1 over 1 is still 1. We have our vertical asymptotes occur whenever the cosine function is 0. So whenever this is 0, that's where we're going to get our undefined points. So every time that cosine hits the x-axis, we have a vertical asymptote. Another thing that happens is whenever we have a local maximum for the cosine function, that's a local minimum for the secant function. And vice versa, when we have a local minimum for the cosine function, we get a local maximum for the secant function. The cosecant function looks very similar to the secant function. The difference is when the sine function is 0, that's where we get our vertical asymptotes. So at 0, and then over here again, we have at pi radians and at 2 pi radians, that's where we get our vertical asymptotes. Again, whenever the sine function is at a local maximum, we get a local minimum for the cosecant. And when sine is at a local minimum, we get a local maximum for the cosecant function. The period for both the secant and the cosecant is 2 pi, just like it is for sine and cosine. So tangent and cotangent are the only two trig functions whose periods are different than that of the sine and cosine. So keep that in mind. So here's an example. It says solve for x if the cosecant value is equal to 2, and we're in quadrant 2 is basically what this is telling us. It says x is between pi over 2 and pi, so we know we're in quadrant 2. So if we know the cosecant is equal to 2, then we also know that the sine function is a half. So remember, theta would be down here. So the sine is the reciprocal, so sine would be a half, and what values of x would give us a sine value of 1/2? Well, that's a 30-degree reference angle, or pi over 6 radians, but we're in quadrant 2, so that must mean we're at 5 pi over 6 radians. That'll do it for this lesson, guys. We'll see you next time.